Imagine being hundreds of feet underwater, sealed inside one of the most complex and survivable warships in service, where mistakes in engineering or maintenance can have catastrophic consequences. Life aboard a nuclear-powered submarine depends on redundant safety systems, constant drills, and crews trained to react without hesitation. In 2025, these vessels face growing challenges: drones, undersea surveillance networks, and adversaries advancing in ways that make hiding harder than ever. How do they stay submerged for months? And how close are new sensors to finding them? To answer that, we first need to look at the fleet itself. The 2025 Submarine Fleet. The US submarine fleet in 2025 is far smaller than the sprawling force fielded during the height of the Cold War, when both Washington and Moscow built submarines at a relentless pace. Instead of competing on sheer production numbers, today's Navy operates with about 64 total nuclear-powered submarines, split between roughly 50 attack submarines, SSNs, and 14 ballistic missile submarines, SSBNs. Though the force is lean compared to Cold War levels, every boat now carries far more capability, giving each vessel a reach and flexibility that older generations could not match. This reduction in numbers might look like a disadvantage on paper, but the calculus has shifted. The priority is no longer massing hulls across every ocean corridor. It's maximizing what a single submarine can accomplish. A modern SSN can deploy with advanced sonar, arrays able to detect and sort contacts at ranges unthinkable in the 1980s. Add in the ability to fire not just torpedoes, but precision land attack and anti-ship missiles at long distances, and each submarine suddenly represents multiple roles rolled into one. Its nuclear reactor allows it to remain submerged for months, limited only by food supplies, and new computing power enables crews to process real-time acoustic signatures with an accuracy their predecessors would have struggled to imagine. Where early Cold War submarines often needed numbers to overcome limitations in endurance and sensors, the modern fleet flips that logic. A single Virginia-class submarine on patrol today can carry out intelligence collection, sea denial, precision strikes, and undersea escort missions simultaneously. The result is fewer submarines covering more tasks with greater survivability and versatility. In short, capability now outweighs quantity. This emphasis on advanced capability has made deployment patterns even more strategic. Attack submarines in the Atlantic chiefly monitor Russian fleet activity and protect key maritime routes into the Arctic, where ice cover complicates navigation and detection. Their counterparts in the Pacific focus on the Indo-Pacific region, where vast distances and expanding Chinese naval activity force the US to carefully position each deployment. Ballistic missile submarines likewise divide between coasts, some slipping quietly into patrol boxes in the Atlantic, others heading into the wide expanses of the Pacific. The guiding principle is the same as it has been for decades. Keep them unpredictable, keep them hidden, and deny adversaries any certainty of where they might be. Managing this force of about 64 submarines, however, is not without strain. Every deployment must be balanced with training, maintenance, and shipyard availability. If boats are stuck in overhaul for months longer than scheduled, fewer remain available for patrols at the same time that global security demands continue to rise. Both Russia and China represent persistent undersea challenges, but China's rapid naval growth in particular stretches the US fleet across larger contested regions. Every submarine assigned to one area means another region has less coverage. Fewer hulls, more responsibility, and greater pressure if yards or crews fall behind. Long-term sustainment also comes down to production. Two programs dominate the future of the fleet: the Columbia-class ballistic missile submarine, which will replace the aging Ohio-class, and the Virginia-class, the backbone of the attack submarine force. These two classes together anchor the Navy's shipbuilding plan, but industrial capacity limits how quickly new submarines can be built. Delays in either program ripple through the entire force structure, underscoring how closely America's ability to project undersea power depends not only on the submarines at sea, but also on the shipyards that maintain and replace them. Strategically, this means each submarine carries weight far beyond its own hull. With only about 64 boats in total, the loss of even one would be felt sharply, both in military value and as a signal to adversaries. To offset that vulnerability, the Navy invests heavily in survivability. Quieter propulsion systems, hardened hulls, and highly trained crews drilled to react instantly to mechanical failures or unexpected contacts. The logic is simple. If each submarine is irreplaceable in the short term, then each must be as close to invulnerable as possible in practice. In the bigger picture, the transformation of the fleet illustrates a paradox. On paper, America has fewer submarines than at any point in half a century. In reality, the force of 2025 commands a level of reach and capability that no competitor can equal. One ballistic missile submarine on patrol today wields the destructive power of thousands of older strategic warheads, while an attack submarine carries enough weapons and sensors to replace several Cold War-era boats at once. Numbers alone no longer define strength. Effectiveness and adaptability now do. The Navy has chosen quality over quantity, but that choice makes understanding the roles of these vessels even more important. The fleet divides into very different kinds of submarines, each built for a distinct purpose. Some take the fight forward, tracking adversaries and striking targets with precision. Others exist to vanish, staying unseen for months while carrying weapons designed never to be used unless the nation's survival is at stake. The difference between these two types of submarines is central to how American undersea power works, and why both are indispensable today. Attack submarines versus ballistic missile submarines. The submarine force is divided in two: the attack submarine, or SSN, the prowling predator, and the ballistic missile submarine, or SSBN, the silent vault. Each fulfills a completely different job, and their behaviors at sea reflect those differences. One is built for speed, stealth, and weapons that strike first. The other is built to disappear, waiting quietly with a payload it hopes never to use. Attack submarines act as the hunters of the deep. They move into contested waters ahead of larger fleets, clearing out threats before crises erupt, and ensuring that US surface ships can operate where they're needed. They are armed with heavyweight torpedoes, Tomahawk cruise missiles, and with the Virginia payload module on newer boats, the capacity to carry up to 40 Tomahawk-sized weapons, an upgrade that has fundamentally expanded their strike role. This makes them flexible. A single SSN can sink enemy submarines, launch precision land attacks, or insert special operations forces onto a hostile coast. Crews drill endlessly in contact tracking and target identification because mistakes in fast-moving environments are costly. Their effectiveness rests on hearing everything without being heard themselves. Ballistic missile submarines, by contrast, are designed for endurance and invisibility. There are 14 of them in today's fleet, all Ohio-class, with the Columbia-class scheduled to replace them beginning later this decade, eventually reducing the number to 12. Their armament is not measured in torpedoes or cruise missiles, but in Trident IID-5 ballistic missiles. Each missile carries multiple nuclear warheads that can reach across continents. Once deployed, an SSBN patrols quietly for months on end, its location known only to a select group of naval planners. Its mission is not to go near adversaries, but to remain at large, extremely difficult to detect, and therefore nearly impossible to eliminate in a single strike. This guarantees what strategists call a credible second strike capability, the assurance that the US could retaliate even if attacked first. The technology upgrades in 2025 reflect these dual roles. Attack submarines now employ sonar systems that use digital signal processing to separate faint contacts from the background noise of the ocean. They can identify signature patterns of foreign ships and submarines with greater speed than crews could manage in earlier generations. When combined with expanded missile payloads from the Virginia payload module, SSNs can execute both intelligence missions and precision strikes at long range without having to approach a coastline. Their prowling nature means they remain forward deployed, close to possible conflict zones, capable of quick and flexible response. SSBNs, on the other hand, have benefited most from refinements in quieting technology. Newer designs use reactor systems that avoid mechanical pumps, reducing vibration. Hull coatings and acoustic tiles prevent the reflection of active sonar pulses, while internal systems are isolated to minimize noise travel through the water. The result is not invulnerability. No submarine can claim that, but a platform engineered to be extremely survivable and exceptionally hard to track. Their quiet operation brings credibility to their mission. They deter nuclear conflict not by what they do, but by making it impossible for adversaries to know where they are. To make this distinction concrete, consider two simultaneous patrols. Near Taiwan's contested waters, an American SSN silently monitors the growing presence of Chinese surface groups and submarines. Its crew notes propeller rhythms, sonar emissions, and radio traffic patterns, building a database of movements. If conflict erupted, the submarine could launch torpedoes against hostile submarines or long-range missiles against shore facilities. Its strength comes from being close, unseen, and ready to attack on short notice. Meanwhile, thousands of miles away, a ballistic missile submarine continues its long, monotonous patrol. Its crew follows strict routines, running equipment checks and navigation drills, but avoids high-traffic regions. They do not seek contact. Their purpose is to sustain endurance under the ocean's cover, maintaining an option for nuclear retaliation that no opponent could eliminate with certainty. Its silence is the threat. The very possibility of its hidden presence discourages adversaries from escalation. When viewed side by side, the missions reveal a simple contrast. Attack submarines project power in conventional conflict. They announce US presence in subtle ways, reminding adversaries that any surface ship or submarine could be marked and followed without detection. Ballistic missile submarines guarantee deterrence by staying submerged and unpredictable, their weapons reserved for scenarios of last resort. The two are halves of one strategy: hunters that secure the seas day to day, and vaults that anchor strategic stability at the nuclear level. Crew life also reflects the divide. On an SSN, sailors work through high-tempo missions filled with constant contact reports and a stream of tactical decisions. A deployment may involve trailing adversary submarines for weeks or operating close to foreign coastlines. The pace is quick, and the margin for error is slim. By contrast, an SSBN crew trains for repetition and precision. Watches can stretch into long periods of routine monitoring where little changes. But every mechanical check must be perfect, because the weapons aboard must remain reliable even after months beneath the surface. One crew lives in bursts of action, the other lives in disciplined endurance. Modern attack submarines are expanding further into intelligence roles. They can launch unmanned undersea vehicles to scout or monitor regions where human presence is riskier. They intercept communications and map undersea terrain, serving as information gatherers before any conflict begins. Their range and adaptability make them more than just combat vessels. They are tools of surveillance, reconnaissance, and forward presence, extending US awareness into contested seas without signaling overt aggression. Ballistic missile submarines change less, but their upgrades focus on staying viable against rising anti-submarine technology. Even as nations deploy new undersea sensor networks and unmanned patrols, boomers improve their reactor designs, hull coatings, and quiet propulsion systems in order to remain ahead. They are not expected to expand missions. Their only task is deterrence, and their continued ability to vanish into patrol areas validates their existence. Understanding this contrast, Hunter versus Hidden Vault, explains why the US maintains both. Removing either half would create gaps adversaries could exploit. Submarines that only hunted could not deter nuclear conflict. Submarines that only carried nuclear weapons would concede control of contested waters. Together, they create a layered security, one part visible through controlled demonstrations of power, another entirely invisible, promising retaliation if anyone miscalculates. But neither the prowling predator nor the silent vault could exist without one shared technology that underwrites everything about their endurance, their stealth, and their reach. Without it, submarines would have to surface constantly and expose themselves. To understand how they can vanish beneath the ocean for months at a time, we need to look inside the system that powers them every moment they are underway. Inside the nuclear reactor. The unbroken rhythm of submarine operations is sustained by one source of power that makes everything else possible: the nuclear reactor. Unlike conventional boats that must return to the surface often, nuclear-powered submarines draw their endurance from a compact reactor designed to run continuously while sealed deep beneath the ocean. Instead of days measured by battery life or fuel reserves, nuclear propulsion stretches that timeline into months. The ability to stay underwater for entire seasons isn't just convenient, it is what makes the submarine survivable. Stealth enduring through time is the real advantage. Nuclear propulsion at sea is not the same as nuclear power plants on land. The massive civilian reactors often associated with skyline cooling towers have little in common with their naval counterparts. On submarines, reactors are built to be compact, self-contained, and able to operate in a closed steel envelope under enormous pressure. They must keep turning without interruption, often for years at a time, while producing enough power to move thousands of tons of metal silently through the ocean. To an adversary, that power source is invisible, but its presence extends the submarine's shadow far beyond what fuel-burning engines could provide. The contrast with diesel-electric submarines shows why this matters. Diesel boats still play important roles in many navies, but their architecture limits them. Every few days they must either surface or snorkel close enough to the air to recharge their batteries. Whenever that happens, the risk of detection from radar or aircraft sensors spikes. The act of surviving becomes tied to routine exposure. A nuclear submarine sidesteps that problem entirely. Seamlessly submerged for months, it eliminates the very signatures that often betray conventionally powered submarines. For decades, submarine reactors needed refueling during their lives. Each cycle involved major overhauls in specialized shipyards, stretching maintenance into months and decreasing fleet availability. Modern designs move away from that pattern. The Virginia class, for example, was engineered to lower the frequency and complexity of midlife refueling, while the Columbia class, the next generation of ballistic missile submarines, takes it further. Its reactor core is designed to last the full service life of the submarine without requiring a midlife refuel. That reduces downtime, improves availability, and shifts the entire maintenance model of the fleet. It also demonstrates how advances in fuel efficiency and reactor control have reshaped the balance between endurance and logistics. The underlying principle remains the same: generate heat from the fission of enriched uranium, transfer that heat into water to create pressurized steam, and use the steam to turn turbines. Those turbines generate electricity and drive the propeller system. What has changed are the refinements around safety, efficiency, and stealth. Modern boats carry overlapping layers of emergency systems built to take over instantly if a component falters. Sensors track temperature, pressure, and radiation parameters with precision, feeding continuous data to trained reactor operators. A deviation from expected performance generates immediate warnings. The result is not a plant running unchecked, but a system built around control and redundancy, never left without safeguards or human oversight. A major evolution in recent years has been the shift toward quieter propulsion. Traditional systems linked steam turbines directly to propeller shafts through reduction gears, an arrangement that introduced both vibration and distinctive acoustic traces. A newer approach replaces that mechanical link with an electric drive system. In practice, turbines generate electricity, which then powers motors that turn the propellers. This reduces machinery noise and creates smoother thrust, making detection by enemy sensors far more difficult. The Columbia class will incorporate electric drive from the start, representing a design focused as much on stealth as on power. For submarines, noise is vulnerability. The less they radiate outward, the more secure their patrols remain. The power created by the reactor extends far past propulsion. Everything sustaining life inside the sealed hull depends on it. Oxygen is drawn from seawater through electrolysis, splitting hydrogen and oxygen so crews can breathe continuously without outside air. Carbon dioxide scrubbers remove exhaled gases to maintain a safe atmosphere. Water required for drinking and cooking comes from desalination plants, again powered by the reactor, converting seawater into fresh. These functions once demanded large logistics trails for surface ships. For submarines, they come automatically as long as the reactor hums. Food, not water or air, becomes the limiting factor. Modern patrols frequently run around 90 days, not because energy is depleted, but because pantries eventually empty. Temperature control also flows from that same power source. Heat within the confined hull builds quickly, not only from the reactor itself, but also from the constant operation of equipment and electronics. Unlike a building on land, a submarine does not shed excess heat naturally. Active climate regulation keeps spaces livable for crew and stable for sensors and weapon systems. Lighting, communications, cooking, and computing all follow the same rule. If it requires energy inside a submarine, it flows from the plant located deep amidships. In that sense, the reactor binds together the warship as an organism. Every function circles back to that single core. Despite the advanced automation and safeguards, reactor operation depends on watchstanders. Nuclear-trained sailors spend years in study and simulation before their posting, memorizing protocols and emergency drills until they become instinct. Their daily work might look uneventful, minor adjustments, close tracking of displays, valve checks, but concentration is constant. The burden is clear. A serious mistake would not only threaten the submarine, but could compromise deterrence and national security. Vigilance preserves the secret endurance of the ship. The unbroken hours of monitoring are the price for silent months at sea. Space inside the hull is another dimension improved by modern reactor design. Earlier generations devoted vast compartments to bulky machinery and shielding. Progress in miniaturization and efficiency has compressed those systems, freeing critical space for alternative uses, additional sensors, expanded weapon storage, or simply less cramped crew quarters. On a platform where every inch carries a purpose, such efficiency magnifies capability across the boat. Another consequence of efficient design is flexibility. The freed weight and space translate into room for payload modules and evolving technologies meant to keep submarines relevant through decades of service. Endurance itself creates paradoxes. Submarines technically could keep moving underwater indefinitely as long as the crew has food. Yet patrols are scheduled with precision. Long deployments stretch human resolve, and extended confinement inside a steel shell taxes both body and mind. Routine maintenance, rotations, and supply-resupply require scheduled returns. Thus, a vessel that could theoretically sail for years between refueling remains tied in practice to quarterly calendars shaped by people more than reactors. The machine is ready. The crew demands balance. By 2025, nuclear propulsion demonstrates how design choices ripple outward into strategy. Reactors that avoid midlife refueling extend availability. Electric drive augments stealth. Life support integration allows missions measured in months instead of days. The overall effect is to give one submarine the ability to patrol far from home waters without reliance on supply ships, tankers, or escorts. Independence in endurance means independence in strategy. Commanders can send boats into contested waters confident that detection will not come from a need to resurface. Quiet power alone guarantees that advantage. It is easy to frame this as purely a story of engineering. The miniature plant sealed inside a submarine hull, circulating quietly while missions unfold. Yet the reactor is also the enabler of what comes next. A submarine with endurance, but no means of force, would remain little more than a science experiment. The energy that powers propulsion and life support also drives the systems that load, maintain, and fire weapons. Every torpedo launch, every missile strike, Every sonar sweep traces back in some way to the same nuclear plant. What transforms quiet endurance into a credible weapon system is how that power supports the tools of combat. Inside the same hull that houses the reactor lie weapons designed for precision and reach, able to threaten adversaries in ways they cannot always see coming.